Okay, so you've sent in a ton of stuff on polar regions and climate change.
Yeah, a lot.
It's a lot.
Absolutely.
And we are going to cut through it and bring you the most surprising and crucial stuff about what's happening up at the ends of the Earth.
Yeah, think of it as kind of like a frozen library, of our planet's past and kind of unlocking that.
Yeah, and what we're going to do in this deep dive is look at the interplay of Iceland and sea in the Arctic and Antarctic.
Right.
And what that ancient history can tell us about our future.
Exactly. And the thing that's so interesting about all this is that scientists, through really incredible dedication and ingenuity, have been able to kind of read these icy pages, if you will, and give us an understanding of this long story of Earth's climate and how it's changed.
Yeah, and it's a story that's really relevant to what we face today.
Oh, absolutely.
One of the things that really stuck out to me from all the stuff that you sent me was this account from an author who was on a video call with his kids back in Cape Cod.
Oh, yeah.
He had just returned from an expedition to northern Ellesmere Island. Now, this is one of the most remote northerly settlements on the globe.
Right.
They call Grise Fjord the place that never thaws out. It's 900 miles from the North Pole.
Wow, that's incredible.
Staggering.
Yeah.
And while he's on the call with his kids back in Cape Cod, these 3 Inuit children pop into the frame.
I love that image.
Yeah, it's amazing.
Yeah, because you have this snapshot of 2 completely different worlds kind of colliding. You have his children in Cape Cod.
Yeah, a familiar landscape.
Right, exactly.
Then you have these other kids in this endless expanse of ice and snow.
Right. And yet there's that immediate connection that he notes.
Yeah, and on a fundamental level, those kids' futures are linked
They are.
through this global climate system we're about to explore.
For sure.
It's a powerful illustration that what unfolds in these seemingly distant polar realms has tangible consequences for us.
For all of us.
So let's head north first to the Arctic.
Okay.
And a physicist named Willie Dansgaard,
Yeah.
who had this idea of a lifetime.
I love Dansgaard's story. It's so interesting.
Yeah.
He's trained in physics in Copenhagen, but just has this draw to Greenland.
Yeah.
And his initial experiences there weren't that glamorous. He actually struggled with housing.
Wow.
He even lost a place to a fire.
Oh, no.
And basically surviving on rye bread oats and lots of chocolate.
I mean,
But those intense Arctic conditions obviously really had a profound impact on him.
he said he was smitten with Greenland for life.
Yeah.
But back in Copenhagen, he found himself in kind of a dull job as a librarian.
Okay.
And then here's where things take an interesting turn after the war with all this influx of Marshall Plan funds. The Geological Institute got a brand new mass spectrometer.
Okay.
And Dansgaard saw this as his opportunity
Yeah.
to dive back into research, even if it meant a pay cut
Wow.
to become a technician on this new equipment.
Yeah.
But it was his way to pursue his scientific curiosity.
And that curiosity led him to his groundbreaking work on oxygen isotopes in water. He knew that you have heavier and lighter forms of oxygen.
Right.
And his big insight was that these isotopes, they behave differently during evaporation and condensation, depending on the temperature.
Okay.
The lighter one evaporates more easily.
Right.
The heavier one condenses more readily in cooler temperatures.
Okay.
And so his question was, could this ratio in ancient water and ice actually be a thermometer for past climate?
It's an amazing leap.
It is.
And he was resourceful.
He was.
He didn't need some, state-of-the-art lab to test this out.
No, he didn't.
He literally used beer bottles in his backyard to collect rainwater throughout the year.
Oh, wow.
Then analyzed these samples with a mass spectrometer and discovered that the ratios perfectly matched the temperatures at which the rain had fallen.
That's so cool.
So low tech.
Yeah.
And it changed how we understand polar regions.
Yeah. It provided a way to read this temperature history that's stored in ice.
Yeah, so all of a sudden these frozen landscapes became these invaluable archives
Yeah.
of past Arctic climate.
Exactly.
But to unlock that long-term history,
Yeah.
he needed a continuous deep ice core
Right.
that spanned millennia.
That's right.
And that brings us to the U.S. military's Cold War project, Camp Century in Greenland.
Okay.
Initially, their aim in drilling this massive, over 4,500-foot deep ice core wasn't climate science at all.
No.
They were exploring building a military base
Mhm.
with nuclear missile silos hidden beneath the ice.
Wow.
But it turned out to be exactly what Dansgaard needed. This continuous record stretching back 100,000 years.
It's amazing how that worked out.
It is.
Yeah.
I mean, access wasn't immediately granted
Yeah.
because of national security concerns.
Heck, imagine.
So it's ironic to think that this climate data was initially guarded as a military secret.
It is.
But eventually, geopolitics,
Yeah.
the U.S. wanting to maintain a presence in Greenland
Right.
and foster good relations with Denmark, led to Dansgaard getting access to sections of this core.
Okay.
So his initial findings were really significant, confirming this warming trend at the end of the last glacial period.
Right.
But here's where it gets interesting.
Okay.
His analysis revealed these rapid warming events within the glacial periods themselves.
Oh, wow.
Sudden spikes of up to 10 degrees Fahrenheit in just a few decades,
Wow.
followed by much slower cooling.
So the Earth has a history of flipping the switch on temperatures really quickly.
Yeah, it's not a gradual dial, it's like a hair trigger,
That's right.
and knowing this natural volatility makes the impact of our current warming even more concerning.
Right. Because it's already volatile.
Yeah.
And now we're adding to it.
Yeah, exactly.
Yeah.
So initially, the scientific community was understandably skeptical of these findings.
Right.
These were dramatic shifts happening way faster than anyone had imagined.
Yeah.
But Dansgaard persisted.
Yeah.
He collaborated with Swiss scientist Hans Uger on a deeper, more refined Greenland ice core project in 1977.
Okay.
And this time, the evidence for these rapid temperature swings was undeniable.
Right.
It became a recognized scientific fact that the Arctic climate system had this capacity for incredibly rapid change.
Yeah.
But the story doesn't end with ice cores.
No, it doesn't.
Around the same time, a German oceanographer, Hartmut Heinrich, was examining cores taken from the floor of the Atlantic Ocean,
Okay.
covering the same period.
Yeah.
And he found something equally unexpected: layers of rock debris
Oh, wow.
within these typical muddy sediments
Yeah.
that had marine organisms.
So these layers were unlike anything usually found in the deep sea cores.
Yeah, exactly. There were 11 of them.
Yeah.
And Heinrich recognized that this rock rubble looked like fragments from eastern Canada.
Huh.
And he hypothesized that massive numbers of icebergs breaking off from glaciers in Canada
Yeah.
had rafted this debris across the Atlantic as they melted,
Okay.
depositing the rocks onto the ocean floor.
So they acted like rafts, basically carrying the debris.
Exactly.
Interesting.
So these Heinrich events, as they became known, were linked to these sudden glacial breakups in northern Canada.
Wow.
And what's astonishing is the speed and impact of these events.
Yeah.
It seems they happened in less than 250 years and caused global sea levels to rise by 3 to 6 feet.
With each event.
Yeah.
That's incredible.
It is.
Yeah.
So the takeaway from this Arctic history is that the system of ice climate ocean currents
Yeah.
has a natural ability
Mhm.
to undergo really rapid and dramatic changes
Right.
long before human industrial activity really started.
And that leads to the question, what happens when we introduce the huge influence of human industry into this already volatile mix?
Yeah. What happens when we add to that? So let's turn to Antarctica.
Yeah.
Historically, the prevailing view of Antarctica was that it was this stable, colossal ice mass,
Right.
a safeguard against, sea level rise,
Yeah.
especially compared to the Arctic, which seems more dynamic.
Right.
And the sheer size and the average altitude of the Antarctic ice sheet.
Right, which is almost 10,000 feet.
Yeah.
Yeah.
Suggested that it would only change with massive warming of the air.
It makes sense that people would think that.
Yeah. And some scientists even theorized that a warmer climate could lead to increased snowfall over Antarctica.
Yeah.
And cause the ice sheet to actually grow in mass.
Right.
In fact, the 2001 IPCC report stated that the Antarctic ice sheet was likely to gain mass due to increased precipitation.
Wow.
So this really shaped scientific thinking for a while.
For a long time.
Yeah, but
Yeah.
the geological evidence revealed a different story,
It did.
largely thanks to the work of John H. Mercer, a glaciologist at Ohio State's Byrd Polar and Climate Research Center.
Okay.
He was a real field scientist,
Yeah.
known for his focus on rocks
Okay.
and his rather independent spirit.
Huh.
And his work on the Reedy Glacier in West Antarctica really challenged this established thinking.
Okay. So what did he find?
So what he observed were these layers of lake sediments containing scattered glacial debris
Okay.
high up on the Reedy Glacier,
Yeah.
dating back 120,000 years.
Okay.
So this led to his big conceptual leap.
Which was?
Well, if lakes existed at such high altitudes, it suggested that the lower-lying West Antarctic ice sheet, much closer to sea level, probably didn't exist at that time.
Oh,
And the implications of that were huge.
they were.
The West Antarctic ice sheet is comparable in size to the entire state of Alaska
Wow.
and holds enough ice to raise global sea levels by about 14 feet.
If it all melted.
Yeah, if it were to completely melt. So his findings indicated that this kind of dramatic melting had happened before during a warmer period.
So how could such a massive and seemingly stable ice sheet melt so extensively?
Well, the International Polar Year 1957 provided a piece of the puzzle.
Okay.
Scientists mapping the bedrock beneath the West Antarctic ice sheet discovered that it sits in a basin,
Yeah.
with much of it below sea level,
Right.
in some areas almost 2 miles deep.
Wow.
And this sub-sea level bedrock is key.
It is.
It means that warmer ocean water can flow underneath the ice sheet
Yeah.
and melt it from below.
Right.
And the large ice streams flowing from the continent's interior are held back by coastal glaciers and floating ice shelves.
Right.
So Mercer theorized that warming oceans could melt these coastal glaciers,
Yeah.
cause the ice shelves to collapse,
Right.
removing the dam
Right.
and allowing the much larger land-based ice to flow into the ocean.
So just to clarify for our listener,
Yeah,
when those ice shelves collapse, it's like removing a dam behind it.
right.
The ice shelf itself melting doesn't add that much to sea level.
Right, it's what it's holding back.
Right, exactly.
That's the potential for sea level rise.
Exactly.
So he presented these ideas in 1968,
Yeah.
but they didn't gain much traction.
Really?
He persisted and published a more detailed paper in 1978
Okay.
and explicitly linked increasing greenhouse gases in the atmosphere to the conditions that caused the West Antarctic ice sheet to melt in the past.
Okay.
And he even made a prediction of a 14-foot sea level rise within the next 40 years
Wow.
due to the breakup of ice shelves.
So was he right?
Well, that prediction was met with a lot of skepticism. Some people even dismissed it.
Right.
He was labeled an alarmist,
Wow.
and his ideas weren't widely accepted at the time.
Interesting.
Terry Hughes, another colleague at Ohio State, also focused on the precarious state of the Pine Island and Thwaites glaciers.
Okay.
Because of their relatively small ice shelves and the warming waters next to them,
Right.
he published this paper, The Weak Underbelly of the West Antarctic Ice Sheet, in 1981,
Okay.
which also faced a degree of indifference.
Wow. So both of these guys kind of ahead of their time a little bit.
Yeah, but then events unfolded that really shifted the perspective.
They did.
Pedro Scarca's analysis of satellite imagery in 1994 revealed significant rifting and recession of the Larsen Ice Shelf on the Antarctic Peninsula.
Okay.
And then came the actual breakups.
Right.
The Larsen A Ice Shelf in 1995,
Yeah.
witnessed firsthand by researchers at Argentina's Matanzas Station.
Yeah.
This massive ice shelf basically disintegrated in a matter of hours.
Wow.
And then even more dramatically, the Larsen D Ice Shelf in 2002,
Yeah.
twice the size of Larsen A,
Wow.
disappeared completely in just a few weeks
Wow.
due to warm summers causing melting from the top
Yeah.
and warmer ocean water melting it from below. So again, it's important to say that the melting of these floating ice shelves themselves
Yeah.
doesn't directly cause a significant rise in sea level.
Right. It's like the ice cube in the glass.
Right.
Right.
It's their role in providing this buttressing effect
Exactly.
that slows down the flow of the land-based glaciers behind them into the ocean.
Great.
That's crucial.
Yeah.
So the loss of Larsen A and B did lead to an increase in the flow rates of the glaciers they were holding back,
Yeah.
though these particular glaciers weren't large enough to contribute massively to global sea level rise.
Right.
The concern is focused on the much larger ice shelves that support these vast glaciers in West Antarctica,
Right.
which hold back enough ice to raise global sea levels by over 16 feet in a century if they collapse.
Wow.
So suddenly the ideas put forth by Mercer and Hughes,
Yeah.
once considered alarmist, are
Right.
now being seen as very real possibilities.
Yeah, they were right.
And the focus intensified on the 6 key glaciers in West Antarctica.
Yep.
That act is these critical barriers, especially the Pine Island
Yeah.
and the enormous Thwaites Glacier.
Right.
Now, if Thwaites alone were to melt completely, it's estimated it could raise global sea levels by 2 feet.
Wow.
But more alarmingly, its potential collapse could destabilize the entire West Antarctic ice sheet.
Leading to that 16-foot rise.
Yeah.
Wow. It's incredible that, Mercer was working, way back when, and now we have the technology to actually see what he was talking about potentially unfolding in real time.
Exactly.
With satellites and underwater robots. It's fascinating.
Yeah, so let's dive into what the recent observations are telling us. I mean, studying these remote glaciers
Yeah.
presents enormous challenges.
He says.
I mean, the distances are vast.
Yeah.
Establishing even temporary research camps takes years of planning
Wow.
and incredible resilience
Yeah.
from the scientists involved.
Right.
But the need to understand their behavior
Yeah.
has spurred this innovation in research methods.
It had.
Eric Rignaut's use of radar interferometry in the 1990s was a game changer.
It was.
Allowed scientists to measure the movement of ice at Pine Island and Thwaites with this millimeter-level precision from space.
So you're talking about using radar waves from space to take precise pictures of the ice?
Yeah,
And by comparing pictures taken at different times, we can see how much the ice is moving,
exactly.
even down to tiny fractions of an inch.
Oh, yeah.
And that tells us a lot about its stability.
Yeah, so this revealed significant rates of retreat and thinning far exceeding previous estimates.
Wow.
Pine Island Glacier was found to be retreating at a rate of over 1 kilometer per year.
Wow, that's fast.
It is.
Yeah.
And then more recently, submersible robots,
Yeah.
like the one used in the 2019 expedition,
Right.
provided unprecedented views of the seafloor in front of Thwaites Glacier
Okay.
and revealed these geological features that indicate really rapid retreat in the recent past.
So faster than the satellites are showing.
Yeah, significantly faster.
Wow.
And then the Icefin robot explored beneath the Thwaites Glacier in 2020.
Right.
And that gave us a more complex picture of melting.
It did.
Showed some areas melting slower than anticipated
Okay.
because a layer of fresh water was acting as insulation.
Interesting.
But other areas, particularly cracks and crevasses, were experiencing very rapid melting.
Oh, wow.
And we're now observing an increasing number of cracks and meltwater pools forming on the ice shelves
Yeah.
that support Thwaites and Pine Island glaciers.
Which sounds familiar.
Yeah, a pattern reminiscent of the pre-collapse state of the Larsen B ice shelf.
Yeah.
So what's critical to understand about this accelerating ice loss in Antarctica is that it's primarily driven by the warming of the oceans.
More so than the air temperature.
Yeah,
Interesting.
and rising global temperatures are intensifying the westerly winds around Antarctica,
Okay.
which are accelerating the Antarctic circumpolar current.
Right.
And this intensified current is delivering more and more warm water to the Antarctic coastline.
Undercutting the ice shelves and glaciers.
Yeah, from below.
Wow, it's just a cascade of interconnected effects.
It is.
Yeah.
So now let's shift our focus to another aspect of this system,
Okay.
the land itself.
The land.
Yeah.
Okay.
Charles Francis Hall,
Yeah.
a fascinating and somewhat unconventional explorer,
Right.
deeply interested in the Arctic and the Inuit people,
Yeah.
learned a lot from their traditional ecological knowledge,
He did.
including their observations of beaches that appeared to be rising over time.
So Hall was ahead of his time in recognizing the value of Inuit knowledge.
He was.
Their understanding of the Arctic landscape built up over generations provided really key insights into these environmental changes.
Yeah, and their observations of these rising beaches pointed to a significant geological process known as glacial rebound.
Glacial rebound.
Yeah, so the weight of these massive ice sheets
Yeah.
pushes down on the land beneath them,
Yeah.
causing it to sink.
Right.
And when the ice sheets melt,
Yeah.
the land slowly rises back up.
It rebounds.
Yeah, and this process can take thousands of years because of the viscous nature of the Earth's mantle.
Okay.
And we see examples of this in Sweden and Finland, where harbors are receding
Yeah.
and new land is emerging from the sea.
Which creates all sorts of interesting legal issues.
Yeah, about land ownership.
Yeah, that's wild.
It is. So glacial rebound is generally a gradual process.
Yeah.
But the rate varies depending on the viscosity of the mantle in different regions.
Okay.
Seismic analyses suggest that the mantle beneath West Antarctica is not particularly viscous,
Okay.
which means that the land, including the seafloor, could rebound relatively quickly.
As the ice melts.
Yeah. So this raises a more optimistic possibility
Okay.
that this uplift of the land could slow down or even counteract the flow of glaciers into the sea.
So almost like tilting a sliding board upwards a bit?
Exactly.
Interesting.
So recent analysis does acknowledge this potentially stabilizing role of land deformation over these long timescales.
Yeah.
But the scientific consensus remains that under high greenhouse gas emissions, the rate of ice loss is likely to outpace this rebound effect.
Right.
Okay, so the collapse of the West Antarctic ice sheet can't be prevented by this alone.
So the land does respond.
Yeah.
But it's not enough.
It might not be enough.
Yeah.
And this underscores the importance of looking to the deep past to inform our understanding of the future.
Right.
John Mercer's work highlighting the collapse of the West Antarctic ice sheet
Yeah.
120,000 years ago.
Right.
And the surge in global sea levels
Yeah.
is a crucial warning.
Yeah.
And the more we look at the long-term climate records, from ice cores and seafloor sediments,
Yeah.
extending back hundreds of thousands of years, the clearer this interconnectedness becomes.
It does.
These records reveal a strong correlation between global temperature changes,
Right.
the volume of ice in glaciers and ice sheets,
Yeah.
and global sea levels.
And often with seasonal precision.
Yeah, it's amazing.
Yeah.
And over the last 400,000 years, There's this striking relationship.
What's
For every 1 degree Celsius of change in global average temperature, sea levels have fluctuated by an average of nearly 60 feet.
that is a huge number.
It is.
Yeah.
And when we look at where we are now on that graph,
Yeah.
our current global average temperature is high,
Yeah.
but our sea levels are low.
Compared to historical data.
Yeah.
Okay.
So this suggests that a significant future sea level rise is locked in.
As the planet adjusts.
Yeah, and some studies project a potential sea level rise of 120 feet in the coming centuries.
Temperatures aren't reduced.
Yeah,
Wow.
and there's some fascinating evidence from octopus genomes
Oh, wow.
that further supports this idea that the West Antarctic ice sheet was absent during past warm periods.
Okay.
Genetic analysis suggests that populations of octopus now separated by West Antarctica interbred as recently as 100,000 years ago.
So they were connected.
Yeah, strongly implying that there was no substantial ice sheet there.
Wow. So the rocks, the ice, and even octopus DNA
Yeah,
point to a future of rising seas.
they do. And with West Antarctica having the potential for the most rapid change,
Yeah.
and contemporary satellite measurements led by Eric Rignod confirmed that ice mass loss from both East and West Antarctica has been increasing since 1979,
Right.
with significant acceleration in recent decades.
Yeah.
And Greenland has also undergone this dramatic shift.
Yeah.
It went from gaining ice to losing ice every decade since the 1980s.
Yeah.
And it's already contributed about half an inch to global sea levels,
Wow.
and most of that in just the last 8 years.
Wow. And the current rates of ice loss are they're alarming.
Yeah, they are.
About 150 billion tons of ice are being lost per year from Antarctica.
And 270 billion tons per year from Greenland.
Yeah. All of that meltwater going into the oceans is going to have huge consequences.
It is, and NOAA's 2022 Sea Level Rise Technical Report highlights this,
Yeah.
noting the 6-inch rise in global mean sea level over the past century
Yeah.
and projecting a further 1-foot rise in the next 30 years.
Okay.
But there's a lot of uncertainty beyond 2052. And the range of predictions by the end of the century is quite broad,
It is.
from a relatively conservative 4.5 inches to a devastating 10 feet.
Depending on emissions.
Yeah, so this brings us back to that image
Yeah.
of the children in Griesfjord and Cape Cod.
All right.
Their seemingly disparate lives are interconnected,
They are.
and they face a future where even modest amounts of sea level rise can have a devastating impact.
Yeah.
And it's not just those two places.
No.
It's coastal communities worldwide,
Right.
from the Netherlands and Denmark to southern Florida,
Yeah.
Bangladesh,
Yeah.
low-lying Pacific Island nations like the Marshall Islands and Kiribati.
And they face a particular irony because they've contributed so little to this problem.
Yeah, and the consequences extend beyond just coastal inundation.
They do.
The influx of cold fresh water from melting ice can disrupt major ocean currents,
Right.
leading to colder, drier conditions in Europe
Yeah.
and warmer, wetter conditions in southern latitudes,
Yeah.
impacting weather,
Yeah.
agriculture,
Right.
and global economies. So
Yeah.
ultimately, the most immediate and dramatic transformations
Yeah.
are in the Arctic and Antarctic themselves,
All right.
impacting landscapes, people, ecosystems.
Yeah.
So we're left with a critical question.
We are.
Considering this inherent capacity for rapid change,
Yeah.
now amplified by human-caused warming,
Right.
how do we reconcile our understanding of long-term climate trends
Yeah.
with the potential for abrupt and catastrophic shifts in ice sheets and sea levels?
It's a big question.
It is, what are the ethical and practical implications
Yeah.
for future generations
Yeah.
and for the vulnerable coastal communities already facing the consequences?
It's a question we all have to grapple with.
Yeah, and this interconnectedness,
Yeah.
revealed through the history held within ice, land, and sea,
Yeah.
demands our attention.
It does.
So keep exploring the research on polar climate and its far-reaching consequences for our shared future.
Absolutely.
Thanks for listening.